Okay, good morning. So let us continue the lesson. So let me just review what we learned last time. So we talked about divisibility. So we say that two numbers A and B, say integers, they are coming from the set of integers. We say that A divides B, or B is divisible by A. What do we mean by this? We mean there exists a Q in Z such that the number on the right is equal to the number on the left multiplied by this Q. So as soon as we are able to guarantee the existence of such an integer so that the left hand side multiplied by that becomes the right hand side, then we are done. So this is what we learned before. We solve some examples, but today I want to solve a little bit more examples together, and then we continue the lesson. Okay, so these examples, I have seen some of these type of example in the book, so this is why it's good to talk about them. So yeah, let me write the example number one. Example. So let A and B be integers such that 13 divides A plus 3B. Yes. Show that or prove that a 13 divides this combination as well, 9A plus B. Okay. So what is the meaning of this question? This question is asking you, if I give you two integers and I guarantee you this condition to be true, then you want to prove that this condition is also guaranteed to be true. So this is the meaning of this. For example, I don't know, can you come up with some numbers that satisfy this condition? For example, take B3, yes? Let us take B3, A to B4, yes? Yes. So if I choose these numbers, hopefully you agree with me, this is a true statement then, yes? Because 4 plus 3 times 3 is 13, yes? And 13 is really divisible by 13. This is one of the possibilities, of course. I don't know, you can come up with a lot of probably pairs of numbers that satisfy this. But now let us check the same pair that I chose there to see here it works or not. 9 times A, 9 times 4 is 36, plus B, which is 3, it becomes 39, and 39 is still divisible by 30. But this is just an example to somehow understand the problem. The problem is not this. The problem is claiming that whatever pair of numbers you choose and it works, for the same pair, this is automatically guaranteed as well. So we want to prove this. Okay, so because you don't have that much experience in these kinds of problems, if you don't mind, let me start describing. Of course, I will ask for your help and then you can contribute, okay? So let me write the solution. So you are telling me that A and B are integers such that that is happening. So it means that 13 divides A plus 3B is guaranteed. Okay, what can I conclude from this one? The only thing that I have in my disposal is my definition. So when you say 13 divides this, what does this mean? This means there exists an integer q. So this means there exists a q in Z such that the number on the right, A plus 3B, is equal the number on the left, 13, multiplied by that q. So this is what I know by the definition. But my goal is to show this is also true. Usually it is always good. You go to a scratch paper. Yes. and then you ask yourself, okay, my goal is to prove this. To prove this, I have to confirm that there is an integer so that when I multiply it by 13, it becomes 9a plus b. So in other words, you ask yourself, is it possible to confirm that a number q in Z exists so that the right-hand side, which is 9a plus b, is equal to 13q? So this scratch work, or I mean, you should do it in your head or write it on a paper. It doesn't mean this is the solution, but now it motivates you what you're supposed to do. You are supposed to write 9a plus b as an integer multiple of 13. Okay, if you succeed to do that, then the problem is finished. So writing this in a scratch paper gives you the idea probably what to do. Okay, so now you have something in your mind, you want to reach to that, but you have something guaranteed is this one. So it means that you need to find a connection, a legal mathematical way to go from here to there. Okay? And it is not that easy. I mean, these kinds of problems, they can be very nasty. So if you change the numbers a little bit, either I cannot solve them or I have to think a lot. Okay? So, but let us think. I'm trying to teach you how to think, because if you know these things, then your chances of solving these kinds of problems will increase. So what is your opinion? This is what you have. If you ask me what q is, I don't know, but I know q is an integer. This is what I need. Even if you ask me what q is, I don't know. I want to confirm its existence. So how can we do that? By the way, the algebra in number theory is extremely simple. There's no algebra involved. Okay, that much. So you see that I have a here, I have 9a there. So it motivates, might be, okay, it's a good idea, let me change my color because still we are not sure. So might be one idea was to add 8a to both sides, yes? You want to make a to be 9a and 3b to be b, yes? This is probably some idea. One way of changing a to 9a is of course adding 8a to it. But I want to keep equality the same, so it should be a legal way of doing this. So when I add 8a to the left-hand side to keep equality meaningful, I have to add 8a to the right-hand side as well, yes? Okay, so far so good. But I don't need 3 b's, I need only 1 b. I have 3 b's. It might motivate you to subtract 2b from it. Okay, but if even I want to keep the same equality, I have to do the same thing on the right-hand side as well. So this is one way of thinking. And if I simplify that, it becomes 9a, this becomes b, it is equal to 13q plus 8a minus 2b. So what I have written on the board, is it true or false? Are you following what I've done? By looking at this, what I need, I try to ask myself, how can I change a to 9a? Because a is what I have, 9a is what I want. So what I want to do, okay, I add 8a. But when I add 8a here, because I want to keep equality the same, I have to add 8a to the right-hand side as well. And here I have 3b, I need 1b, so it motivates me to subtract 2b, but when I want to keep equality, when I subtract something here, I have to do the same thing on the other hand. Okay? So what I have written here is true or false?
True.
True, okay? But this is one of those truths which is useless. Yes? It is true, what I have written. Why? So you might think that no, it is not useless because then I can factor a 13 out. Let us factor 13 out. So let me go further. If I factor a 13 out, this becomes q. This becomes 8 over 8 over 13. That's correct, because if I multiply this back, 13 and 13 are cancelled, and I get my 8a back. Okay, and then I write minus 2b over 13. So is this also true or false? So everything that I have done here algebraically is sound and clear, yes? But then you might say that, okay, now I call this my Q and I am happy now because my goal was to show that 9a plus b is 13 times a number Q. And if I call this number Q, then I have my goal and I am done. Okay, do you think that this conclusion is correct or not? Whatever I have done algebraically is completely correct. But the last conclusion, that from here I can conclude that this number is divisible by 13. Is it true or false? Yes? Do you understand what I'm saying or not? Yes? Yeah.
You can't prove that that is an integer.
Yeah, exactly. So that is the whole point. I can call it whatever I want to. I can call it capital Q, but I told you that I have to confirm that what I call capital Q is an integer. I cannot confirm that this is an integer. Why? Because I don't know A and B. Might be 8a is not divisible by 13. If it is not divisible by 13, then it is not an integer. And if it is not an integer, when I add it to an integer, the result is not an integer either, yes? So what I have done, I want you to understand, algebraically is 100% right. But if you want to conclude this from the very last statement, it is not working because this includes fractions. And if you have fractions, it is not guaranteed yet. It is an integer. It's a whole number. Is that clear? Yes or no?
Yes.
Okay. So, unfortunately, we were close to solve the problem, but we couldn't. So we cross it over. Yes? Or if you think you can save this solution, you need to show me why 8a over 13 is an integer, and you need to also show me why 2b over 13 is an integer. If you somehow miraculously can do that, then of course I agree with you. Then this problem is finished. Yes? My goal is not to tell you exactly what to do, but I want you to understand, if something written like this, it is not enough to conclude this. Yes? Okay. Okay. Apparently, the algebra was reasonably correct, but we reached to this dead end. Okay. Then I have to come back and revise my solution and find a new strategy. Okay. Do you have any other idea what to do? Again, you should have a goal towards that. Again, the same thing. I have this in my hand. I want to go from here to here. One way of going from here to here was adding and subtracting appropriate terms, but it didn't work. Okay? Is there any other way that I can imagine I can go from here to there? Might be it works this time. So algebraically, it is, by the way, at the level of maths 1C, algebra is at that level. Okay? But it doesn't mean that you shouldn't blame yourself if you cannot find a solution at the level of Math 1C, because the thinking is not at the level of Math 1C. Okay? So a plus 3b, can you give me another way so that I can go there? Okay, so remember, I have my gun at your head. If you don't say something, I will shoot. At least it is better to say something. What do you do here? Yes?
You can try division.
Division by what? Division is not a good idea from the beginning. You know why? Because I want to avoid divisions as much as possible. So yes?
Can we factorize A and B out?
So what is the point? A and B out, what does it mean? So factoring A out means A 1 plus 3B over A. This is what I understand from what you say. This means factoring A out. Okay, so then what? Okay, say something else. Okay, finished? Your tools are finished? So you see, A plus 3B. So you might think that I want to fix both things, yes? But don't think about two variables. Okay, we cannot apparently fix them. So let us say that I want to fix only A to look right. So what should I do? Yes?
You put the B on the other side.
It is 2B on the other side, or B, because still I need my B on the left. That's what I'm saying. This is the reason that you write this in a scratch paper, because you see that you need A and B both on the left-hand side still. So if I ask you just fix A to be 9A, one way of fixing A to be 9A was adding 8A. Another way of fixing that is, yes? Multiplying, yes? So let us multiply. Okay. I come from here, but because this will work, so let me write the solution with black, okay? So I have A plus 3B is equal to 13Q. Let me multiply by 9, okay? When I multiply the left-hand side by 9, it becomes 9A. And if I multiply this by 9, it becomes, unfortunately, 27B. But I have to live with it, yes? I cannot just throw this away because I don't like it, yes? And then I have to multiply this by 9. You don't need to really multiply, so let me just 9 times 13 times Q. If you want, of course, you can multiply. Okay? So is this algebra is correct? Yes. So the previous algebra was right. The new algebra is also right. The previous algebra apparently was not working, but this is why we changed our strategy. This time we multiplied 9. And when I multiplied 9A, this is why. You have always look at what you want to reach. 9A is good because I have it and I need it. But unfortunately, I need only one B. How many B's I have? 27 B's. Then I need to think again. I want to make it B. So now what do you think? Yes? Yes, 26 B's. Yes, so what I do is this algebra also right? So then you see, it is not very random. I'm not saying it is a straightforward, but we are not doing things randomly because we have a goal in front of us. So then on the right-hand side, I have 9 times 13 times Q. And then when I subtract 26B there, I have to, if I want to keep equality the same, and I have to subtract that. Okay. And then what happens, this becomes 9A plus B. But on the right-hand side, it seems that I have a little bit of mess there, okay? But this mess works. The previous mess didn't work. Why this mess works? Yes? You can factor 13 here. Yes? So what happens now? This implies that 9A plus B, I factor 13 out. What is left? 9 times Q minus 26 divided by 13 is 2. So so this is what I'm saying. There is no guarantee that it was working. The nature of the numbers was in a way that this was working. Yes? And then I do not have any fractions at all. So can I now call this capital Q and be happy? Yes, because you are telling me that Q, little q, is an integer. In the problem, they are telling me that B is an integer. So if Q and B are both integers, I hope that you agree with me. If I multiply this one by 9, multiply this by 2, and subtract them, still it is an integer. There is no reason to have a fraction. So here I can call it Q. Here I could call it Q again, but I don't have any guarantee that this Q is an integer. But now this Q is guaranteed to be an integer. Yes? So this Q belongs to Z. So what happens? It means that this number is an integer multiple of 13. Okay, so this means that 13 divides 9A plus B and B. Is that clear? But I agree, this is not that easy that much. Sometimes I also have to do a lot of trial and error to find the correct combination that allows me to go from one to the other. Yes?
Is it guaranteed that there's always going to be a right combination, or do you have to?
No, if the person who has designed the question means that the person has a solution, so it means that yes, it is guaranteed.
You have
Yes.
to try.
Yeah. I mean, so this is a problem we solve, but what the question that you're asking is how to design such a problem. Yeah, it's not probably that hard, and this is one of those problems. The reverse engineering of it is hard, but making it probably is not that hard. So you can make up these combinations, and then the people who are doing number theory, they have other tools that they can think about these problems simpler, and then express it in that. So is the logic clear? Okay. I will give you another one. This is harder. Okay, but let us see how it works for you. Okay. So example. This is harder. I will let you to think about it, but after a while, if you couldn't, I give you the hint. By the hint that I will give you and the experience that you got here, then I wouldn't consider it hard problem. Okay, so let us see how it goes for you. So I would say that let A and B be integers such that this is the combination. 17 divides 3A plus 4B plus 2. I show that 17 also divides this combination 7A minus 2B minus 1. So I want you to think about the problem. Okay, think about it 2 or 3 minutes. If you have an idea, please share it with me. Otherwise, I give you a hint and wait for you again. After the hint and this experience, I think you should be able to solve it if you have listened to me carefully. Okay, any progress? Okay, so let me the starting point, by the way, is not hard. So let me write solution. How do you write the starting part? So you say that, okay, this is guaranteed. So you are telling me that 17 divides 3A plus 4B plus 2. Then according to the definition that I have, I can conclude that there exists a cube in Z such that the right-hand side number 3A plus 4B, yes, plus 2 is this number on the left multiplied by that cube. So this is the translation of the first sentence in mathematical symbols. That's what we know. Okay, again, you can go in a scratch work. Yes, you can see that what you are supposed to show. You are supposed to show this. How can you achieve the goal? If you can show the number on the right, minus 2b minus 1 is is an integer multiple of 17 where q belongs to z, then you are done. So you know what is your goal. You have this expression, equality. You somehow want to reach to this equality. Okay? Do you have any idea how to do it? So I will use this color, so might be that's not correct, so I will fix it later. Yes, what should I do?
You multiply both sides by minus 2.
Here you multiply by minus 2, so it becomes minus 14a plus 4b plus 2. So you see, we can ask him, how did you understand that? So this one multiplied by 2 or that one?
No, this
No,
one.
you cannot start from here because this is what you want to show. Yes?
Okay, but I guess you can do the other way.
No, this is just a guess. No, you want to show this one. Yes?
Yeah, but I mean, if you can multiply by minus 2, you can just do something.
No, be careful. This is a very important problem in logic. This is you don't know it yet. Okay? You want to prove it, but I want to see. So let us finally go what's happening. So you say that this is, I take it for the granted for the time being, because this is not granted yet. This is what we want to show. Do you understand that? So we don't know if it's true or false, but you are using it. So it means that you are momentarily assuming that, let us assume that this is true, and let us explore what is happening. This is a good idea, but at the end, you shouldn't fall to this trap that is your proof. Do you understand what I mean? Because this is something we are still don't know. We want to show this is true, but you are using it. Yes? So let us see how it goes. So you said that take this one multiplied by -2, it becomes minus 34q. Okay, then
You add 17a on both sides.
17a. So let us just do it in my head. If I add 17a, becomes what?
3a.
3a plus 4b plus 2 is minus 34q plus 17a. Then?
And then I just factored out 17.
And then you factor out 17. So, and then what happens? It becomes a minus 2q. Okay. And then what? And then you see that, okay, a minus 2q is an integer. Yes? And then you are done. Because you reach to what you know. You see the logic is not clear. It might be helpful. What you have done, it might help you to find the real proof. But I want you to know that this is not proof.
So
yes?
Always work on the other one.
No, not always. I want you to understand what is going on. If I say the truth of P is guaranteeing the truth of Q, you are proving that the truth of Q is guaranteeing the truth of P. Okay? And this doesn't mean that, I told you before, we talked about implications before. So if x is 3, x squared is 9. Okay? If x squared is 9, there is no guarantee that x is 3. So if I ask you to prove this, instead of proving this, if you prove this and say that I am done, this is not enough. Do you understand what I mean? Here, this statement is your assumption to be true. This is called the premise. And this is the conclusion. What you have done might be helpful to discover the real proof, but still it's not the proof. So you have taken this for granted, and you have shown that if this is true, that is true. But there is no guarantee that if this is true, that one is also true. But you are getting close if you can come up with some idea from it.
Yeah.
Yes? So what should we do now? Actually, this is helpful now. So what you have discovered is useful, but if you can use it. So how can you use that? Remember, you have to start from here and little by little reach to there. Now you have a very good discovery in front of you. Yes, so can you use what you have done? Yes? Everyone understands that why the logic is not correct here. Because he's saying that if this is true, yes, I guarantee that this one is also true. But the problem wants you to do the other way around. If this one is true, we want to show that one is also true. Yes? Can you find a way yourself? Okay, let me give you a hint. So could you save your solution? It might be possible, but I want you to understand, might be, let me correct myself. What I write as a scratch paper, it doesn't mean that I have it. It means I want to reach to this. The reason that I write on a scratch paper, because I want to see it in front of my eyes. So if I replace these two, your solution is for that problem, and that's completely correct. Yes? But now we want to go the other way around. Either you use this idea to be able to reverse engineer your solution, so that you go back to that. That is possible, if you think probably. But the way that I want to describe, and I want to wait again, so what I will do here, so let me clean this. And I am telling you that, so let me say, multiply everything by 8. After that, you should be able to do it. Okay, so what I say, let me change my color. So I conclude from here, I multiply everything by 8. It seems very strange number, but let us see how it works. If I multiply by 8, it becomes what?
24A.
24A plus 32B plus 16. And I don't even need to bother to multiply, I just write it like this, because you know the goal is to factor 17 out at the end. Might be this is a little bit hard, but after that, if I provide you with this hint, in principle, you should be able to do it. Okay, so I want to wait again for you. Yes, because now you see, this is why this is the reason that I put it in a scratch paper in front of my eye, so that I can know where I am supposed to reach. Yes, so now you understand that. You see that you have 24 A's, but this is not what you want. What you want is 7 A's. Okay, so then I don't think it is hard for anyone to do that. How can I do that? So I write 24, instead of 24A, what can I write? I can write 7A that I need. But this is 24. I need 7A. What is left for me is 17A. So it gives me how to break it up, yes? Because in principle, 24, I can write it as A plus 23A. I can write 2 plus 22A. Why did I choose to write 7A plus 17A? Because in a scratch paper, I see that I need 7A. Yes? And now, can you tell me what to do with the next one? Here I have 32 B's, but what I need is minus 2B. So it motivates me to write minus 2B. Okay, can you tell me what should I write next? Because I want to compensate to go back. 32B, I am taking it off. I am writing minus 2B. I have to compensate for that change that I am making by, yes, plus 34B's, yes. No one will criticize me, yes, because these two will be combined to the same thing. So if I take this off and write this, that is okay. But how on earth I realize to do that? Because I see my scratch paper, I need minus 2B. Okay? Okay, again, once more. I have 16, I see my scratch paper, I need minus 1. So what can I write now? Instead of 16, I write minus 1, but I have to compensate that change by adding 17. Okay? On the right hand side, I have 8 this way. And then you see again a scratch paper. In a scratch paper, you have only this expression on the left. So this motivates you to keep that expression on the left. And what you don't need, what do you think I will do? 17A is something that I don't want to have. 34B is something that I don't want to have. 17 is the same. So what do I do? Do you think? Yes? Move everything to the other side. Yes? So like a garbage. Yes? So I will write them, all of them there. Yes? So let us see what happens. But hopefully you now understand this is solving the problem. So you see, I moved this one, it becomes minus. I move this one, it becomes minus 34. I move this one, it becomes minus 3. So this now, what happens here, 7A minus 2B minus 1 is equal to. Now what do you think I will do here? Because again, I see my scratch paper, I need 17 standing alone multiplied by an integer. So this motivates me to, if possible, factor 17 out. So I factor 17 out. So what is left from this one? 17 is pulled out, 8 times q is left. 17 is pulled out, minus a is left. 17 pulled out, minus 2b is left. 17 pulled out, minus 1 is left. Now, of course, I can always call this something new q, but is this q guaranteed to be an integer now? Yes, because the little q was an integer, and A and B are integers according to the problem. So this combination that doesn't have any fractions, and Q, A, B, and are integers, so that's an integer. So this belongs to a set of integers. So then what happens? This expression is an integer multiple of 17. So what is the conclusion? The conclusion is that 17 divides 7a minus 2b minus 1. Yes? Okay, so this is one way. I'm not saying, by the way, this is the only way. When I was teaching this problem in technique group, they found another way. Okay, that's also complete. And I think your method will also work if you try to reverse engineer what you did so that you can go from the other direction. Yes? I would recommend you to think about it. Okay, let me solve one problem from the PDF file that we are following as a book. This is the problem in the book. So example, so this is the rule of divisibility by 3, for example. If I want to know if a number is divisible by 3 or not, one method, very simple method, is to add the digits, and if the sum is divisible by 3, it guarantees that your number is also divisible by 3. For example, if I ask you, is this number divisible by 3? So 12,345. If I want to see that, I take the digit 1, 2, 3, 4, and 5, and then add them up. It is much simpler than this number, because 3 plus 3 is 6, 10, 15. Is 15 divisible by 3? Yes. This guarantees that this number is also divisible by 3. Yes? But we want to see why. Okay? In the book, they have discussed it for 3-digit numbers. So let us stick to the book. So the point is that we have a 3-digit number. By the way, when you say ABC in algebra, people read it as A times B times C. But when I write a 3-digit number, I don't mean 1 times 2 times 3, I mean 123. To make it clear, we put a bar on it. If you put a bar on this, it means that A is a digit, B is a digit, 3 is a digit, not A times B times 3. Okay? So my goal is to show that if A plus B plus C is divisible by 3, prove that the 3-digit number A, B, C bar is divisible by 3. This problem is in the text of your book. And I think it's a good rule to remember. Let me just, okay, so why do you think this is correct? This is a little bit simpler than these problems, but of course, you see, again, this is a completely new problem. The idea is more or less the same, but as if it is a complete new problem. So how should I solve the problem? So we want to show that this rule is not a coincidence. This rule always works. Yes. Can you speak louder, please? Yeah, so that was the idea. So every 3-digit number, for example, when I say 253, do you agree 253 means what? 200 plus 50 plus 3. Do you agree? So this is the meaning. So can you say that if I want to follow the same rule, ABC can be written as what? 200 means this digit multiplied by 100. 50 means this digit but multiplied by 10, and then the unit number. Okay, so if I give you a 3-digit number, you can write it as 100 times this digit. So it becomes 100A. And then this digit plus what? 10 times B plus C. So you see that if I give you a 3-digit number, hopefully you agree with me that you expand it like this. This is always true. Okay, now what do I have at my disposal? I know that a plus b plus c is divisible by 3. So if you don't mind, let me write it next. So we know that a plus b plus c is divisible by 3. What does it mean? It means that there exists a q in, so let me write like this. This in mathematical notation means 3 divides a plus b plus c. This is the translation of this English sentence, yes? A plus b plus c is divisible by 3. This means what? This means there exists a q in Z such that the number on the right is equal to the number on the left times q. Okay? And now, for the next one, again, you can go to a scratch paper. So this scratch paper is the creative part, yes? So you have A, B, C, then you understand it yourself that this is 100A plus 10B plus C. You need to show that this is 3 times Q for Q and integer. So this is your goal, yes? I want to show that this 3-digit number, which can be written in this form, is also an integer multiple of 3. That is what we want to show. To show this is divisible by 3 means exactly what we have described here. So what can I do? So again, you have something in a scratch paper in front of your eyes. You have something at your disposal. You need to find the ways, you need to try the ways that might take you from this to this. But in this case, it is much simpler than the examples I mentioned there. Anyone else? Yes?
Can you multiply it by 100?
So if you multiply it by 100, might be that's good. I don't know. Let us follow yours, okay? So you say that by looking at the first term and the experience you got so far, you might think that it's a good idea to multiply everything by 100. Let us check. So if I multiply everything by 100, I think it will work. Let us see. That's what I'm saying, that even though this is a new problem, but your experience has increased, so your chances is getting higher, okay? So what happens? You told me multiply by 100. Is it legal? Yes. As far as I multiply both by 100, both sides by 100, that will work. Okay, so this becomes, let me write 300, it's easy. 300 cubed.
Now we subtract.
Exactly. So you tell to yourself that here I have 100B, but in a scratch paper you have it in front of your eyes. What you need 10B. Okay? So exactly the same experience. So I don't need to touch this first term because I need it exactly there. But instead of 100B, I can write 10B that I need. But I cannot just change it to 10B unless I compensate for the change. What is the compensation here? I need to add 90B to it. And then I look here again. 100C is not what I need. What I need is just one single C, but I have to compensate for that by 99C. And then I have 300 Qs, okay? Now what I need is what? This I need, this I need, this I need. So these are my garbage. So I will put them the other side. So 100A plus 10B plus C is equal to 300Q, and then I have what? Minus 90B, and then minus 99C. Yes? And then what is the goal? The goal is that you have to have a 3 out. So this also motivates you to how to continue. So you write 100A plus 10B plus C, and then on the right hand side you know that you have to factor it 3 out. And then you know that this should end up with an integer. So fractions is not a good sign. Unfortunately, everything is divisible by 3 because this becomes 100Q, this becomes minus 30B's, and that becomes minus 33C. Is that right? So then what happens? Can I really, of course I can always call it Q, but am I sure that Q is an integer here? Yes, because Q was an integer. A, B, and C are digits. Digits are integers, yes? So, and of course this combination is an integer. which is the crucial part. And then what can I do? I can say that, okay, this number is 3 times an integer. So this means that this number is divisible by 3. So this means that 3 divides 100a plus 10b plus c, which of course means this 3-digit number ab. Yes? So now you see that we have 3 problems. The nature of the problems are more or less the same, but it demands a little bit more creativity, okay? And for the same reason, the same rule will apply for divisibility by 9. The book probably hasn't talked about that, but do you think that the same thing will work for 9? So I would recommend you at home solve the same problem. So is this number divisible by 9? The rule is the same. You add the digits, it becomes 15. Is 15 divisible by 9? No. So you can also make sure that this is not divisible by 9. So the rule for divisibility of 9 and 3 is the same. Okay? Okay. Any questions? This was the problem exactly in the book. Okay, so now let us see what we want to do now. We want to talk a little bit, yes.
What level problem is this?
I didn't see, this is solved in the text.
Oh,
It's not in the end of the book.
yeah.
So it is in the, when the author is teaching you this topic, this is an example in the book, so it isn't mentioned. But probably it would be A level, I think, if you didn't know about that. Yes. Okay. Any questions here? Is that clear? Okay, now the next lesson we want to talk is prime numbers, but of course prime numbers you already are familiar with, but I just want to give you some information here. And there is no proof for these things here in the book, so we want to actually understand them as an information. I'm passing you some information about prime numbers. Okay, so if I have a prime number, what is the definition of a prime number? So a natural number or an integer, it doesn't matter here. A natural number p but greater than 1. So it doesn't matter if I say an integer greater than 1 because it means the same thing. And a natural number p greater than 1 is said to be a prime number if the only positive factors of p are 1 and p itself, or an equivalent sentence. So in simple form, it means that p is divisible only by 1 and by itself. For example, 7 is a prime number because 7 is only divisible by, of course, is 7 divisible by minus 1? Yes, it is also divisible by minus 7. So this is why I have mentioned only positive factors, okay? So 7 is a prime number because if I ask you what are the positive factors of 7, you will tell me 1 and 7. Yes? Nothing more. So, and then you know that we have a list of prime numbers. The smallest prime number is the only odd even prime number. No other prime number can be even. Why? Yes?
Because all even numbers are divisible by 2.
By 2. So if the number itself is not 2, and definitely it is divisible by 1, it is divisible by itself, and if it is even, it will also be divisible by 2, which is violating the condition of being a prime. Yes? So 2 is the smallest and the only even prime number, and then I have 3, and then I have 5, and then I have 7, and then I have what? 11, 13, and then if I want to write the list, what is the next one? 17 and 19, 23, and then of course we can continue. The prime numbers that differ by 2, they are called twin primes. So 5 and 7 is a pair of twin primes, 3 and 5 is a pair of twin primes, 11 and 13 are twin primes, and I think it hasn't been proven yet how many twin primes we have. Yes? No, that's a good question, and then you see that I have excluded one. I will come back to it why, okay? So Euclid actually to 400 BC or something, I don't remember exactly the date, he was able to prove that the number of prime numbers is infinitely many. So it was not trivial at all. So why do you think there should be infinitely many prime numbers? Because this is a little bit counterintuitive, yes? Because when you go further and further and the number becomes bigger and bigger, intuitively you think that the chance of this number be divisible at least one number before that increases, yes? So this is at least my intuition. When I go higher and higher numbers, because then I think that, okay, if I have a very big number, it become more probable that it is divisible by something before that. But apparently, we can have infinitely prime numbers. So the list of prime numbers is proven and it is guaranteed, is not finite. You have infinitely many prime numbers. But we haven't discovered a formula in a closed form that generates all the prime numbers one after the other. And as far as I know, we haven't even generated a formula that only generates prime numbers. Yes? So we haven't done that. So this terminologies I want you to know, so you should know that the number of prime numbers is infinite. There is a conjecture that are there infinitely many twin primes as well? We don't know. Okay? That's a conjecture, so we don't know it's true or false. Conjecture means that we don't have any proof for that. I don't know how much. I haven't been updated myself about this, but I don't think, because this is a very famous problem. You should probably hear from it in the news or something if that is being proven. Okay. So the other thing is that why do you think p greater than 1 is not a prime number? Because in principle you think 1 should also be a prime number. Yes? If I ask you what are the positive factors of 1, you say 1 and itself of course 1. So in principle we think that 1 should be a prime number. The reason that they don't take it as a prime number is because of something else. The something else is there is a theorem that is called fundamental theorem of arithmetic. The proof of it is not hard, but the book doesn't include that, so you just need to know it. Fundamental theorem of arithmetic guarantees that any natural number can be written as a product of only prime numbers. Yes? So if I take 7, of course, if a number is prime, let me fix it. Any non-prime number, by the way, there is a name for it, it is called composite. A number greater than 1, which is not a prime number, is called a composite number. Okay, so what is the content of this theorem? This theorem tells you that any natural number that you pick greater than 1 is itself a prime, or if it is not a prime, it can always be written as the product of prime numbers. Okay, so for example, 21 itself is not a prime number, but I can write it as 3 times 7, and 3 and 7 are prime numbers. Okay, this is called the factorization of 21 into prime factors. So if you write your number as a product of prime numbers, which is always guaranteed to be possible based on this theorem, that is called the factorization of the number into the prime numbers. Okay, and then this theorem also claims that if the order of these numbers doesn't matter, then this factorization is also unique. So if I ask you factorize 21, you might say 3 times 7, your friend might say 7 times 3. But that is it. They don't have that much difference. Yes? So The only difference that might happen in your factorization and your friend's factorization is the order of the prime numbers that you write in your product. If you ignore that, your answers are quite the same. Yes? Now let us see why mathematician has chosen not to choose 1 as the prime number, because if you choose 1 as the prime number, you lose the uniqueness part of the theorem. And uniqueness in mathematics is more important than just choosing 1 number to be prime or not. Okay, why we will lose? Because if, let us assume that 1 is also a prime number, and I give you this in the exam, and I ask you to write this as a product of prime numbers. Your friend might be write this, you yourself might be writing it like this. Yes? Because if 1 is a prime number, this is a product of prime numbers, that's also a product of prime numbers, both of them are equal to 21. So then I have to admit that this is correct, this is also correct. Another friend of you can come up and write 1 times 1 times 1 times 3 times 7. That's also a factorization. Then I will have it, I cannot talk about the factorization. I have to talk about a factorization. And usually this is not good. If we can make something unique, mathematicians prefer to give a name to a specific concept. So then I am sure if I ask you this in the exam, write 21 as a product of prime numbers, either you write that or you write 7 times 3. And if you respect the order from a smaller number to the bigger number, then everyone write exactly the same thing. Okay? So this is why the price that we pay, so we want to keep the uniqueness of this theorem. The price that we have to pay is to exclude 1 from being a prime number. Yes?
Then is 1 a composite?
It's not a composite because it fits the definition of a prime number. It fits the definition of prime number because we don't want to lose the uniqueness. We excluded that. Of course, it doesn't make sense to put it in the other category. So 1 is neither a prime number nor a composite number by definition, by convention, if you like. Yes? So if someone asks you why 1 is excluded, now you can answer, because you want to keep the uniqueness part of the fundamental theorem. Yes? So nothing you will gain. If you want to put 1 as a prime number, you will lose the content of the factorization. Then I have to ask, write a factorization. It is better to consider something unique. Yes? Okay, so that is it. If I give you a number, for example, 251, let me ask you this question. If I ask you if this is a prime number or not, in principle, what do? You need to check if this number is divisible by some number smaller than that. There is no reason to check the numbers after that, yes, because it cannot be divisible by 300, by a number. So let us try to see what is the algorithm. So if you want to do that, you need to check 251 if it is divisible by numbers before that. Yes? But do I really need to check all the numbers before that? Yes?
Don't you only have to check 2 if it's divisible by 2?
No, if it is not, then you have to continue, of course. I mean, how many numbers you divide to guarantee that this is not a prime number or is a prime number? I don't want to give the... Yes, you can go. Yes. Pardon? Okay, I can wait. So what you are saying is probably true, yes? But the point is that if I want, then I have to have a list of prime numbers before that. If I already have the list of prime numbers before that, then I know what about 21. That's why this is good, but I mean this is not practical. What I was to say, yes?
Only up until the square root of 251.
No, this probably you know something else. We will come to this. But naturally, you don't need to divide by the numbers bigger than half of this number. Yes, this is the very crude algorithm, yes? So the half of this number is approximately 125.5. I don't need to check the divisibility of this one by 126, 127, yes? Because if it is half, it is already giving you a fraction when you divide them. So there is no point I divide this. So if I divide this by, I don't know, 127, because 127 is more than a half of this, yes? So it cannot be an integer when I divide that, okay? But what you are saying is actually another algorithm that we will discuss about that later, because the lesson is probably finished now, yes? Okay. Or no? We have 10 minutes? I always forget. Okay, 11:30. Okay, so let me continue a little bit. So in principle, I don't need to divide 251 by the numbers before that, before half of it. Sorry, after half of it. But there is another algorithm that an ancient mathematician actually invented, okay? And that is so let me, if I remember the spelling. So the sieve. So you know sieve, what sieve is, yes, in English? I don't know what is this. You put the spaghetti and the water is going out, yes? So the sieve of era. Let me check the spelling. Eratosthenes, yes? So let me, so the pronunciation is Eratosthenes, yes, but the spelling is this one, yes. So he came up with a better and more efficient algorithm. He said that, okay, if you want to see that if this one is prime or not, first take the square root of this number, okay? So can you tell me what is approximately this? 15 to power 2 is 225, 16 to power 2 is 256. So this number should be somewhere between 15 and 16. So let us say this is approximately 15 comma something. Yes? Now you need to find only the prime numbers less than or equal to this number. Okay, what are those prime numbers? 2, what? 3, 5, 7, and 11 and 13. You just need to check the divisibility of this by only these 6 numbers. So you don't need to check that much. If it is divisible by one of them, then it is a composite number. If it is not divisible by these 6 numbers, he was able to show, don't look, there will be no chance that this is divisible by any other number. So it is a very more efficient method, yes? So, and then this is not hard. Is this divisible by 2? No. Is it divisible by 3? We learned today, yes? 2 plus 5 plus 1. Is that 8? 8 is not divisible by 3, so this is out of the list. Is it divisible by 5? Out of the list. And then you have to check only 3 numbers. So if this number is divisible by these 3 numbers, one of them, then of course it is not a prime number. If it is not divisible by this list, he showed that don't look. It is not possible that this is divisible by any other number that you haven't checked. Yes, it is guaranteed that then it becomes a prime number. Yes, is that clear? Okay, let me also show you this in GeoGebra. And by the way, there is a competition to discover the biggest prime number. Okay, it's not that easy. You might say that, okay, this algorithm is really obsolete when it comes to finding the biggest number. It's also good to see it. So let me also show you this. So the biggest, let us check, I don't know what is that, the biggest prime number discovered, yes? Yeah, this is the biggest number discovered so far, okay? So 2 to the power of 82 million and something minus 1. And this number has 24 million digits. Okay, so this is extremely, extremely big. So even if I take the square root of it using this old-fashioned method, this number, the power would be around 41 million. So 2 to the power of 41 million is a very huge, 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 huge number. You cannot even imagine. So if you have 2 to the power only 64 papers, you can calculate it yourself. Let us say that I have 2 to the power only 64, let alone 82 million, okay? If I have 2 to the power of 64 A4 papers and I put them on top of each other, you can immediately calculate it yourself with calculator. the height of this pile of paper will be more or less 6,000 times larger than the distance from the Earth to the Moon. Sorry, the Earth to the Sun, which is 150 million kilometers. Okay? So 2 to the power of 64 is so huge, so that if you put something like a paper, which is very thin, the height of this tower of paper will be approximately 6,000, or I don't remember, 12,000 the distance from the Earth to the Sun, which is 150 million kilometers. Now you can imagine what happens if the exponent, instead of 64, turns out to be 82 million and something. It's a very, very huge number. And then you see that this number has only 18 digits. But that number has 24 million digits. It's a very huge number. So hopefully you understand that this is not the algorithm they used to discover that number. This is not the algorithm. Okay, something else that I want to mention is it's good to use GeoGebra somehow for this course as well. So you go to CAS view. When you open GeoGebra, you have some different views. This is the algebra view, and then you graphic view, and then you go to CAS view, and then you can ask some questions. For example, it's good to know about these things. So this is the syntax, is prime, yes? So you choose is prime, this number, and then I type my number there, and then I press enter. So it is true. So is this number prime number? The algorithm says that this is true. So that was true, yes? So the number that I chose here is true. And something is good also to know. For example, in GeoGebra, you can also write sequence, okay? And then this is always a good thing to choose. Expression, variable, start value, end value, increment. So for example, if I want to generate a sequence, so for example, let me write 2 times n, okay? My variable is n, my starting value is 1, my end value say 20. Let me go a step, two step at a time. So increment means 2 step at a time. Then I can generate the list. So you see, instead of n, GeoGebra plugs 1, generates 2, and then goes 2 step further. It becomes 3, and put 3 here, it generates 6. And then you can do it, and the last one, and you calculate this. Yes? For example, using GeoGebra, there is also another rule. So you can say keep if. Yes, so keep if. Yeah, it is not a Python language, but it is probably similar to the syntaxes you use there. So condition and variable list and everything. Okay, so if I want to say that, okay, is true, is prime, because that is exercise in the book. So is prime, okay, and I write, for example, variable k here. And then I choose variable k. And for example, I want to list all the prime numbers from 1 to 100. So I will write 1, double dot, and then 100, okay? So this tells you that if this statement, if this condition is true, keep it. It is the meaning keep if, yes? If this turns out to be true, keep it. And this 1 double dot is 100 is the list of numbers from 1 to 100. So, and then hopefully it will work, yes. So it listed all the prime numbers less than or equal to 100 for you, okay? So this is good because there are some exercises in the book, it needs probably calculators and things, so you can use these things. And then you can Google things around, okay? For example, I don't know, I think there is next prime. Yes, you see next prime. I don't know, for example, let me write 19. What is the next prime after 19? Is 23. So something like this. But I mean, keep if is prime is a good thing to know about GeoGebra for this lesson. Okay, any questions? Okay, have a nice weekend. Thank you. Just wait.